So now that we know what a central angle and an inscribed angle are, what we're going to do is we're going to realize that there are some properties that connect the two. So the first one that we're going to talk about is that the central angle and the inscribed angle have a property, and they're like radius and diameter. Radius is half the diameter and diameter is twice the radius. Well, the exact same thing happens with a central and an inscribed angle. An inscribed angle, this angle right here, will always be half of the central angle if it's if it's subtended by the same minor arc. Okay? Always, always, always. So if this is 40 degrees in here, this has to be 80 degrees in here. It always has to be a 2-to-1 relationship. Okay, so that's number one property. All the inscribed angles are congruent. That means they are the same measure. So again, if I'm talking about arc PQ, it doesn't matter where we go on the major arc PQ. Has to be on the major one though. Doesn't matter where I go, as long as I start at Q and I end at P. As long as I start at Q and end at P, all of these angles that are inscribed are the exact same. So if PTQ is 20, if this is 20, then this is 20, and this is 20. They're always congruent as long as you have the same minor arc. Okay? And then kind of like what we did at like the semicircle one, if my minor arc, in this case our minor and our major are the exact same measure because we have a diameter and we have a semicircle. If this is 180 degrees right here, that has to be 90. So it's just using the central and inscribed angle property, that the inscribed angle is always half that center angle. In this case, if it's a straight line, this is 180 degrees, so that has to be 90. So any inscribed angles that is subtended by a semicircle are always right angles, always. So we can use we might be able to use Pythagoras theorem in there because we learned that in lesson 1 and lesson 2. Okay, so this is the unit that if you do more examples, your mark will probably be better. So let's go through a couple examples. Once again, is this the one? Oh yeah, this is the one I can't really turn over because I take all of them with me. Here is my minor arc, GF. Notice that here is my central angle because I start at G, I go to the center, and I end at F. So X, maybe I'm going to type this. I really need to get that pen working instead of you guys hearing all this clicks. So angle GOF is a central angle. Angle GHF is an inscribed angle. Okay, inscribed. So therefore, there's that 2-to-1 relationship. So if I want to find angle GOF, that will equal to 2 times angle GFH. Okay, so now I use my pen. So 2 times 28 degrees is equal to 56 degrees. So angle GOF is equal to 56. A 2-to-1 relationship, just like the radius and diameter. Here I have an arc TR, and I know that because if I go to the center and if I draw, it starts at T and ends at R. That's how I do it, but I mean, different teachers teach differently. So I know that that's my arc. Okay, so I go to T, I go to O, and I go to R. So my central angle is angle TOR. My inscribed angle is angle TSR. Okay, noticing that when I name my angles, my T and my R have to match my arc, TR. T and R has to be my first and my third letter. I know that there's a 2-to-1 relationship. I know that this one's twice as much as that. So angle TSR has to be half of 84. So half of 84 degrees is 42. Okay, now let's see this one. I have an angle here and I want to find this one. So I want to go here, E, and then F. Okay, so it looks like this is my arc right here. Okay, so I'm going to erase all this. That's just always my check. Nothing's going to the center. Nothing's going to the center, but here's my arc. It's a good idea just to draw on your arc so you know what you're dealing with. Okay, so angle DEG, let me just put in my angle, DEG is inscribed. Angle DFG is also inscribed. We know that they're equal in measure. All inscribed angles, it doesn't matter what the arc is, as long as the arc is the same. So as long as my starting point and my ending point are the same, these angles will always be the same if they're both inscribed. So angle DFG is equal to 72. Okay. Now those are fairly easier ones. They get a little bit more elaborate, so let's just do a couple more. Here we want to find angle X and Y. Okay, so let's find our arc first. It looks like I have a central angle. Okay, so there's that. My starting point at my center is AB. My starting point at this angle is AB. And my starting point at this angle is AB. So this must be my arc. I know I'm subtending by arc AB. Again, subtending means my start and my finish. Okay, so now let's talk about my angles. So angle ACB is inscribed. Angle ADB is inscribed. And we know that inscribed angles are equal when they are subtended by the same arc. And angle AOB is central because it goes to the center. Its pit stop is at the center. Okay, so let's talk about these. Angle ACB is 55. So since this one, ADB, is inscribed, it's also 55. They're always equal. And since this one is central, I know it's 2 times the inscribed one. So 110. Okay, you with me so far? Okay, let's go through another one. Always feel free to, pause, rewind, and watch the example again. Okay, so what am I seeing here? I am seeing that I need to find angle O. Okay, so it looks like I have a central angle here. So my start is that. That doesn't help me because if this is my arc, there's no other start. Well, I guess. I know that that and that are going to be, there's going to be a 2-to-1, but I don't have either one of them. Okay, so I have to use some other properties here. Okay, well, what else do we do? Oh, look, we have a diameter here. So I know that this angle right here, so angle ACB has to equal to 90 degrees. Because remember, if I have a diameter, and if it starts and ends at the diameter, then that angle in there is 90 degrees. Well, you're probably asking, why does that help us? Well, we have to go back to what we learned in the first unit, first or second lesson. We have ITT here. We have that isosceles triangle theorem. So we know if this is 25 right here, then the base angle of our isosceles is 25. Okay, so that means that this angle right here is 75. Sounds good? You guys all with me so far? Now, because of ITT, again, that isosceles theorem, because this is a radius and that's a radius, that makes x equal to 75 because our base angles have to be the same. And I'm talking about triangle OBC. OBC. It's an isosceles triangle. Okay? So base angles in an isosceles triangle always have to be the same. Now there's a couple ways you can solve for y. I'm going to just say, well, I know that if this is 75 and that's 75, this has to be 30. So triangle angle BOC has to be 30 because I know that the triangle, all the angles in a triangle equal to 180. Okay? Now this line right here, y has to be 180 degrees minus 30 because a straight line, like if I have this, and if this is 30 in here, I know that this has to be 150. Okay? Because they're supplementary angles. And I think you learned about supplementary angles in grade, 5 or 6. So that's how you would find y. So that's a little bit of a different example, but again, you have to pull all the knowledge that you know about angles of a triangle, what do you know about isosceles triangles, what do you know about the angles of straight lines, and you have to pull it all into one example. Let's go on to the next one. Okay, I already know that I'm going to pull it. To me, I like my diagrams pointing up. So again, I'm going to turn my page so that all my, all my angles are pointing up. I don't know why. If you don't like that, just keep it the way it is. It's not a big deal. Okay, so I have an I have an arc here, AB, and I know that's the one I'm talking about, or that I want to deal with because it has a central angle and an inscribed angle that start and finish at AB. You guys see that? So I know right off the bat that x is equal to 100. X has to equal to 2 times 50 because of that inscribed central angle property, that they're 2-to-1 relationship. I know that x is equal to 100. I also know, and I'll erase some things now because you don't need all these lines in here, that if this is 100 degrees in here, I'm going to talk about triangle. Now I'm going to look at triangle AOB, the triangle, not the angle, the whole triangle. And I know that it has to add up to 180. I already know one of them is 100. So the other two have to add up to 80. So these two right here have to add up to 80. And I know, because of ITT, isosceles triangle theorem, that I have to divide it by 2 because I know that those two base angles are equal. So y and z are both equal to 40. Oh, why am I writing x? I say y and z and I write x. So y and z. So a little bit easier of an example. Again, please feel free. There's only so many diagrams that you're going to get on your assessments. They're just going to be rotated or the numbers are going to be changed. But this is a very, very common type of diagram. So make sure that you use all of your tools in order to answer the question. Okay. Oh, a couple more examples. Now, I always tell my students, so I hope this helps you as well, that if you ever run into problems, it is always a radius issue. You need to draw a radius in. And I don't know if this is the example here, but I always tell my students that and I want to share that with you. So rectangle ABCD has its vertices on a circle with radius 8.5 centimeters. The width of the rectangle is 10 centimeters. What is its length? Give the answer to the nearest tenth. Okay, so to me, my first gut's telling me, to connect A to O. And I know that this is also going to be 8.5 because it's a radius. I know that this is 10 centimeters. So now, the word rectangle kind of gives it away because you have to have a 90-degree angle, but I'm going to show how this ties into this lesson. Is because of this right here, CA is a diameter, and this angle right here is subtended by the diameter. It starts and finishes on the diameter. So this has to be a 90-degree angle, and that's one of the properties. Any angle that is subtended by a diameter is a right angle triangle. So because of that, I can actually use Pythagoras theorem. So that is my C. Here's my A, and I'm solving for B because I want to find the length. So B squared is equal to C squared minus A squared. B squared, I'm going to need my calculator, which I do not have. Darn it. Okay, I'm going to try to find a calculator on my iPad here. Oh, maybe I have a calculator. Okay, just hold on here. Because I am not smart enough to do these calculations in my head. Calculator, go. Okay, so C squared. So my C squared, my hypotenuse, is 8.5 times 8.5. So that is 17 squared minus 10 squared. And I should know 17 squared, but I don't want to make a fool out of myself. So 17 times 17, 289, that's what I thought. 289, and 10 squared is 100. I'm going to do my subtracting, and I'm going to get 189. Now, in order to get rid of the square, I have to square root. So B is equal to 13.747, and it wants it to the nearest tenth. So B is equal to 13.7, and my units, always attach them, is centimeters. So that is the length, rounded to the nearest tenth. Okay, one last question here, you guys. Hint, hint, hint. This question always appears, so please pay attention. So what you guys need to know in this example is that there are 360 degrees in a circle. So if I go all the way around a circle, there are 360 degrees in it. You learned this in grade 7. I'm just refreshing your memory. So see how I have here, if I start at A and I go 100 degrees, and then I go 140, well, if I finish the circle, I have to go 360. So the very first thing, is in order to solve for x, I'm going to use that property. I'm going to go 360 degrees minus 100 is 260, minus 140, so 260 minus 140 is 120 degrees. Okay, so now I'm just going to erase this so I can see it. Now there's just a whole bunch of ITTs going on here. Okay, so I'm going to rotate, because I just like everything pointing up for some, like I said. So this is 120 in here, so now let's solve for y. Because of ITT, that isosceles triangle theorem, I know that my base angles are the same. Okay, so I know that 180 minus 120 gives me 60. But now I have to divide by 2 to give me 30. And again, I don't know why I wrote down y when I was calculating z. So z right in here has to equal to 30, because 30 plus 120 will give you that triangle. Okay, sounds good? I'm going to erase this, and I'm going to flip this around again. Okay, so I like my, again, everything pointing up. So why is all of that angle? It's pretty clear in there that it's from here to here. So I have to find that angle, and I have to find this angle. And then I have to add the two together. So I'm going to find this angle by using this triangle, AOB. And I'm going to find this little angle by using triangle BOC. And then I'm going to add them together. So I kind of have to do the exact same thing twice. So let's do 180 minus 100. I'm going to get 80 degrees. I have to divide it by 2 to give me 40. So I know that in here, this is 40. Oh my goodness gracious. It's Saturday morning. 40 degrees. So I'm going to do the same thing here with this triangle, triangle COB. So 180 minus now 140 gives me 40. And now I'm going to have to divide by 2 to give me the 20. So y is both of those angles together. So 40 plus 20 will give you 60. Sounds good? And again, the more examples you do, usually I have a summary. For some odd reason, I don't have a summary for this one. But try number 4, 5, 6b, 8, and 11 in your textbook. Let me know if you have any problems, and I hope this helped out.